Hello, welcome to Science, Mr. Robertson, continuing with pressure right now. And this time, pressure from water pressure, Wattentryck, or from the air pressure, Lufttryck. So, we're going straight on into this, and we've got to talk about water pressure to start off. Now, water makes a pressure. Of course it does, because water will press on you. There was a question last week about if you were swimming underwater, and if you go deeper, you will feel a bigger pressure. Of course you do, because all of this water is also pressing on you now. This water here is pushing on your body. So the further you go down, you will actually find the deeper that pressure is. And I can also work out how much that pressure should be. Because if I have like a bottle which is 10 centimeters by 10 centimeters by 10 centimeters, okay? We remember that is going to be a 1 litre big bottle. We also remember 1 litre is the same as 1 kilogram if it's pure, perfect water. Now, 1 kilogram will be about 10 newtons. So, if I have something here that is 1 litre in size, there is going to be an extra 10 newtons that are going to be pushed from it. It actually gives it a little force upwards of 10 newtons. This is why some things float and some things sink. Let's go in more detail. So here, let's say I had something like this here. Let's say I had a 1 litre object here which was full of oil. Now I know if it's full of oil, it should be about 0.8 kilograms or 8 newtons. So I would have 8 newtons going down. However, if I was going to have, you can see that's 8 newtons down there, times by 10, can you see? Can I move it? 8 newtons. There you go. And then upwards would be 10 newtons. But that would mean it would go up. It doesn't go up, it stays in there. So it only goes a little bit in. So it's 8 newtons down and 8 newtons up. I get a force that balances. So I would find here that my oil would just be a little bit in and a little bit over, like so. I don't need all. I could have 10 because it's making the water go up. And the water would be 1 kilogram equals 10 newtons. But I don't need it all. It doesn't push 1 kilogram of water up. So my up thrust here is equal. If instead of it being oil, if I had, let's say, 1 litre of iron, which is maybe what, 5 kilograms, so 50 newtons, that's 50 newtons down. And the maximum is 10 newtons up. What does that mean? It means it is going to sink. The water pressure isn't enough by itself. Remember, it's easier to swim in the Dead Sea with all the salt, because the salt makes it more dense, so maybe it's not 10, maybe it's 11. The iron will still sink. No doubt the iron will still sink. But there might be a little bit more of this force here. And this force from the water pushing anything up is something I call an up thrust. Eureka! Now, a practical example of us using our water pressure, there's 2 of them to talk about. One is a very famous thing. We have loads in Sweden, actually. It is a water tower. Vattentorn. Super, super useful, super important. It is full of water. Yay. And then I have down here, I have all of my houses. All connected up. Lägenhet också. And what happens is that, remember, the water here can go down. And it could go down and it could fill all of these houses. So all of these houses could be covered in water. Got some water, some blue. I could have all of this come down here and just fill this house up. It doesn't work like that. It stays in the tubes. And it doesn't make any more pressure in any place. What I get is the water's always staying through the pipes. We'll go to the house, we'll go to the house, we'll go here, and it will fill every space here that is below the water level. So I have to build my water tower to be above everything, so that then the water can flow. Even here, it will start to flow upwards, because the pressure is coming from here, so it's still lower down, so it can still push it up. But if I build up here, that's got to be way too high, so I would need to pump here. But at this level, the water will always try and fill each gap it can, even those it has to go up into. It can still do that if it's below the water tower level. Another really cool example is actually in your brakes. Especially those, you can have them in bikes or in car brakes. So of course I have brakes, and we use a system called hydraulics. And it uses our pressure equation. P equals F over A. Because the pressure has to be the same in the water. With water, pressure is shared. It is the same on one side to the other, because I can't squash my liquid easily. If I squash one bit, it squashes the other bit. If I try and push my bath water, it will push away and just keep moving. It doesn't fall through, it just moves. Water can't be pressed at all very easily. So, I can use this in a system like here. Here, this is where I actually have the brake. So the brake pedal on my car or on my hand here on riding a bike, and I push here. Now, it's quite small. So I have small force here and a small area. So just a tiny force, like this here, gets my bike to slow down. But what that does is that little force and little area I take over here, where I have a big force over a big area. By pushing a little bit on one side of the liquid, I push loads on the other side. So riding my bike, press the brake a little bit, means that the wheel here, with the big area on the back wheel, big force, stops my bike. Really clever system, so that I can actually slow down easily. This is called hydraulics, using a small force in a small area to control a big force over a big area. Quickly, we should talk about air pressure. And of course, if I have my earth here, then there's more pressure here than up here. Here there is less, because here I've got more and more air particles that push down on you. The more that is pushing down, the more the pressure is going to be. The difference with water to gas is that a liquid, I can't push it. I can't squeeze my liquid together very easily. It tries to move, tries to break, it's very hard. But I can squeeze a gas. Think about a balloon. If I have a balloon and I blow it, I am making there more pressure inside. What I do is that I put more and more and more air in. So there's more air inside than outside. And remember, that air is moving around. So the more the air moves around, the more the pressure is going to be. Here, what I've done is I've made it overpressured. It's overpressured. There is more air inside than outside. It's really good for things like bikes, for example. You want your bike wheel to be overpressured so it stays stable. It keeps enough force so it keeps round as possible to go fast on your bike. You know how hard it is to ride a bike with a flat tire. This is really good. Another way to get something overpressured would be to increase the temperature. If I make something hotter, then this here is going to move around much more. If it's moving around more, it will trick much more on the outside. It will press it more. It will press it harder. So that will also make more pressure. That's why if you have a balloon, don't put it next to a fire. It will pop. The opposite, of course, of being overpressured is if I am underpressured. Under pressure. And if I want to be underpressured, then what I should do is take out air. And the biggest example we do this is actually if we do something called vacuum packing. So if you get food where, for example, all of the air has been taken out and you just have a very tight bit of plastic that has been vacuum packed, it means I can make the food and the area, volume of it, as small as possible. It can help it last longer. But I've taken all the air out, so there's more pressure outside and it presses in. Let's draw it a little bit here. So if I have, my little thing here, and I have air here, but I have air, 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 air. There's more pressure outside going in than there is inside going out. So it'll squeeze it and make it as small as possible. Big video. Hope it helps you. Thank you very much.